Hello everyone, my name is Ricardo Mendes and I'm here to present the paper entitled Impact of Frequency of Location Reports on the Privacy Level of Geo-indistinguishability. I'll start with a brief introduction and motivation and then talk about the methodology taken for our experiments and then show you the results and respective analysis and finish with the conclusion and future work. So, as you know, or probably know, location privacy has become an emerging topic due to the pervasiveness of location-based services. However, untrustworthy location-based providers that may share or publish the data, eavesdroppers, and security breaches can cause disclosure of location data. And location data is quite sensitive, as it can reveal habits, routines, religion, and even health conditions. So to preserve privacy against this range of attack vectors, we require location privacy preserving mechanisms, or LPPMs, at collection time. That is, these mechanisms act before the data leaves the collecting device. And so these mechanisms give the user control over the trade-off between their privacy and utility instead of relying on other entities. Depending on the LBS, location data can be reported either continuously or sporadically. However, there is no formal nor quantitative distinction between sporadic or continuous reports, and thus this distinction is often based on the type of LBS, on the type of the service. However, this frequency of reports directly impacts the temporal correlation between reports. And in turn, this correlation can be used by an adversary to track users over time and even predict future locations. And in fact, in the sporadic scenario, LPPMs consider reports to be independent from past and future locations, and thus their privacy evaluation may actually be over-evaluated. So they are estimating the privacy level. In this work, we argue that the consideration of independence between reports depends on the frequency of updates. And to evaluate this premise, we quantitatively studied the impact of the frequency of reports in the privacy and utility in both sporadic and continuous scenarios. We focus on geo-indistinguishability, which is a formal notion based in differential privacy that limits the amount of knowledge gained by an obfuscated observation, independently of any background information that an adversary may have. For the methodology, and as I've just said, our main objective is to quantitatively study the impact of the frequency of reports in the privacy and utility of geo-indistinguishability. And to do so, we used the following methodology, and this is just an overview. And what we did is we have this GPS data, which is actually data from real mobility data. And we applied several subsamples, and these subsamples depend on a delta T, which I'll explain in a little bit. And after having this subsample data, we apply or we obfuscate the data using a geo-indistinguishable LPPM. Okay. To the obfuscated data, we then apply localization and tracking attacks to have the adversary estimated data. We evaluate or we measure the quality loss as the utility. We use the quality loss as the utility metric, and we use the estimation error as the privacy metric. So the GPS data that we've selected three highly continuous datasets. We have GeoLife, cab spotting, and portocabs. While GeoLife has a variety of transportation means, both cab spotting and portocabs correspond to taxi trajectories. The GeoLife contains a sampling rate of approximately 1 to 5 seconds, and the cab spotting has 10 seconds, and the portocabs has a 15 seconds sampling rate. Okay, and to this dataset we apply the bounding box and only over the most dense areas, and only the data inside this bounding box was used. So for the subsampling, as I've said, we've applied multiple subsamples to each of the datasets. We did this by suppressing reports such that the minimum interval between two reports is at least delta T. For the cab spotting and portocabs dataset, we used delta T as 60 up to 600 seconds, so 1 minute up to 10 minutes, and this is our continuous scenario. We define this as the continuous scenario. Recall that there is no such formal definition, it depends on the application. And then for the GeoLife dataset, we set delta T as from 8 minutes up to 15 days in an exponential growth, and And we call this our sporadic scenario. So because we wanted to challenge the consideration of independence between reports taken when designing LPPMs, and in the sporadic scenario, we considered the planar Laplace, a geo-indistinguishable LPPM. And this LPPM guarantees statistical indistinguishability within a user-defined radius. And this property is inherited from geo-indistinguishability. And it simply consists in adding noise to the real location drawn from a two-dimensional Laplacian distribution with the following formula. The only variable here, if you look at the formula, is the distance between the user real point, which is x, the user real position, and z, the obfuscated position. And then we have the term epsilon, which is the same as the epsilon in differential privacy. Now, you probably know that the term epsilon is the privacy budget, and just as in differential privacy, properly setting this epsilon value is still an open problem. However, in geo-indistinguishability, epsilon has been traditionally set as L, the privacy level, divided by R, the radius where the privacy level L is guaranteed. Okay, and the user can therefore set L and R according to his requirements of privacy and utility. Decreasing the epsilon results in an increase of obfuscation and consequently a decrease in the utility. For the localization attacks, we've used the optimal attack, giving a mobility profile in LPPM, sorry, and the optimal attack is an optimization problem in where the adversary tries to minimize the estimation error. This attack is optimal, as I've said, for a given mobility profile and an LPPM. For this attack, we've considered two variants: the optimal variant, in where training data is used to build the mobility profile, and this corresponds to a realistic adversary. And we also used the omni, in where we use test data to build the mobility profile. This corresponds to an omniscient adversary, and this is essentially a privacy lower bound, or is typically considered to provide a privacy lower bound. We then also used the attack profile estimation based attack, or PEBA, or PEBA. So in this case, this is a novel approach in where the true mobility of the user is considered unknown and therefore learned a posteriori. That is, the mobility profile is estimated after each observation. The original work presenting PEBA showed that PEBA had better results even than the omniscient adversary. We'll see that our results also confirm these findings. Okay, so for the tracking attack, we've considered map matching as a tracking attack. And map matching is the process, for those who don't know, is the process of continuously identifying the position of a vehicle on the road network, giving noisy locations or noisy location readings. However, we thought of map matching as a tracking attack, and we believe this to be a good approach. And in this, we consider that the output of LPPM is the noisy observations. And then the LPPM assumes Gaussian noise, but it can be adapted to specific LPPMs. So the output of the LPPMs is the noisy observations, okay? And trajectory reconstruction is a general adversary objective in where the adversary, after reconstructing the original trajectory, can then use more general attacks or more specific attacks on the reconstructed trajectory. Because the adversary error is a point-to-point metric, it fails to capture how well the trajectory is actually reconstructed. And because between each 2 points or each 2 locations, multiple paths or segments can exist. And thus, this metric can be erroneous from the point of view of trajectory reconstruction. Therefore, in the case of map matching, we also consider the F1 score as privacy and utility metric. This metric uses these equations and essentially uses the length of the output path, output from the map matching, the length of the original trajectory, and the length of the overlap between the two to compute the score. For our results. For our first set of results, we have, and it's for the GeoLife datasets, we have here the adversary error for the localization attacks. And from left to right, we have the optimal attack, the omniscient attack, and then the PEBA. Okay. Each color is a different epsilon, and in x-axis we have the delta t. Okay, and the first result that we can observe from these three plots is that the delta t has no influence in the adversary error for the localization attacks. So in fact, the adversary error is more or less linear, disregarding for the delta t value. And so the consideration of independence, and this is a conclusion that we have drawn, is that this consideration is actually valid in the sporadic case. We have other results that we'll show you next that will also confirm this to be the case. The second result that we can observe here is that PEBA outperform the optimal attack and even the omniscient adversary. And this result validates the results from PEBA's original work, PEBA's original work, sorry, and thus this confirms that estimating the mobility profile from observed data is a more efficient approach than training a mobility profile, or assuming that the mobility profile of the user is known, okay? However, we can also see that for the last two delta t's, the PEBA did not outperform the omniscient adversary, even though it did outperform the optimal attack. But the reason for this was that the testing dataset was actually smaller due to the subsampling that we did, because the interval, the delta t, the minimum interval between points was too high, so the trajectories were quite short. For the third and last result from these graphs, we have that the epsilons equal or higher than 8 kilometers minus 1 corresponds to having no privacy protection, even though they do incur inequality loss. You can see from the plots that only epsilon values from 1 up to 4 have a non-zero adversary error. And to further validate this conclusion, we also plotted the privacy loss as a function of the utility loss, as we can see in the next slide. So this is also for the GeoLife dataset. It's the privacy versus utility, or the adversary error versus the quality loss matrix. And the first conclusion that we have from this graph is that there's a relationship between quality loss and adversary error, which is linear, but only after a threshold. And this is in contrast with PEBA's original work, where they said that the relationship is linear. But what we've seen from these results and from the previous results is that there's some values of epsilon where the user has no privacy at all, even though it incurs in an average quality loss. And this can be seen from the values of epsilon of 8 and up. The other result is that there's a similarity between the curves of the different delta t. That is, there seems to be no significant impact of the frequency of updates on the adversary error. Therefore, the assumption of independence between reports holds in the sporadic scenario, and this is our first major conclusion. Now, before going into the continuous scenario, we also evaluated the effects of the grid resolution in the adversary error, because these attacks consider a certain grid, and depending on the grid, they can be more effective, more precise, or less precise. So we did this for the gap spotting dataset and for a delta t of 300 seconds for performance reasons. And what we achieved was the following. So we have the three localization attacks from left to right, the optimal, the omni, and the PEBA. And what we can see here is that, so we have the average adversary error as a function of the cell resolution. And as we diminish the cell resolution, as we have cells, smaller cells, we observe that the average adversary error diminishes too. So, and the first conclusion that we've seen here is that there's a linear relation between the cell resolution and the adversary error. And thus we confirm, or we conclude that a resourceful adversary can potentially defeat obfuscation by using a very small cell resolution. The other observation that we can see here is that an increase in the obfuscation results in a decrease of the slope. That is, for lower epsilon values, to obtain the same reduction in the adversary error, a higher reduction in the cell resolution is required. We can see an example here where we have the red line. So with epsilon equals to 16, the adversary needs to use cells of 100 meters to achieve an error of 75 meters. Whereas for the remaining epsilons, the same error of 75 meters is achieved with a 200-meter cell resolution. So this leads us to the interesting conclusion that the privacy budget, and this is from the point of view of the user, the privacy budget can be seen as the computational power required to an adversary to compromise his privacy. And this is another conclusion that we've drawn. Now, the next slides show the results for the continuous scenario, in where we use the cap spotting and porto-caps datasets, as I've mentioned before. This first set of graphs show the adversary error for the map matching and the tree localization attacks for the cap spotting datasets. Similarly to the first results in the GeoLife, this is for the case of the cap spotting, in where we added on the leftmost graph the map matching results. The first result that we have here is that the map matching actually has a lower adversary error than the localization attacks. And we were not expecting these results, but the justification for this is quite simple. This is due to the high values of epsilon and the grid resolution that we used. Because we used such high values of epsilon, most obfuscations and such a big grid resolution, most of the obfuscations that we had were inside the same grid where the exact user location was, and therefore the errors in our localization attacks were higher. But we can see if we, for instance, reduce the grid resolution, and we've seen in the previous graphs, and I've highlighted now here, we see that we can achieve lower results with the localization attacks. All we need to do is either reduce the cell resolution or increase the obfuscation. So the second result that we have from this set is that, again, there is no apparent effect of the delta t in the adversary error. As you can see, it's a linear line here again. So this again confirms that the frequency of updates does not have an impact in the privacy level, but in the case of the continuous case, and as I've said before, the adversary error is not an efficient or effective privacy metric for tracking attacks, because the trajectory can be quite different and the adversary error be the same. So we've evaluated the F1 score as a function of the frequency of reports. And what we have here is the results for the cap spotting dataset and the porto-caps dataset. And in here we can see actually that the frequency of report does have an high impact in the F1 score. As you can see, as the delta t increases, the F1 score decreases greatly in an exponential manner. So for the continuous case, the impact of the frequency of reports is actually significant. We can also see that the decrease in epsilon, which means an increase in obfuscation, decreases the F1 score. So this leads us to the conclusion that lower values of epsilon can compensate for higher frequency rates. So from the point of view of the user, if the application or the service has a high frequency rate, it can increase the obfuscation to compensate the privacy loss of having a higher frequency of updates. So to conclude our work, and a summary, the frequency of updates has a low impact in the privacy level, and the independence between reports can be safely assumed in the sporadic scenario. Under the continuous updates, this is not the case. However, higher obfuscation can compensate for higher frequency rates. The relationship between quality loss and adversary error is linear only after a threshold, as we have seen. And the adversary error is linearly correlated with the cell grid. A powerful adversary can potentially defeat the obfuscation produced through planar Laplace. The privacy budget is inversely proportional to the computational power that an adversary must employ to compromise user privacy. As future work, we want to evaluate the effectiveness of online LPPMs designed for the continuous scenarios under varying frequency of updates, as in this work we only use the planar Laplace, and we want to formulate a relation between the effectiveness of location attacks measured by the adversary error and the value of epsilon. We also want to propose a dynamic LPPM that takes into consideration the frequency of updates to adjust the privacy and utility. Thank you very much, and if you have any question, please feel free.